Greetings, esteemed team. I'm Michael Day.
And I'm Shane Collier.
Today we stand before you with a sense of excitement and responsibility as we delve into a transformative decision that will shape the trajectory of our manufacturing capabilities. The winds of change are upon us with the advent of 3D printing, challenging the very foundations of our conventional manufacturing methodologies. The choice between conventional wax patterns and investment casting is not merely a decision, it's a strategic move toward innovation and efficiency. Join us as we navigate through the capabilities, advantages, and limitations of each approach, coupled with a comprehensive analysis to determine the manufacturing readiness level of 3D printing in our production facility.
The capabilities of 3D printed wax patterns extend beyond the physical. They represent a leap in precision, customization, and design intricacy. We're not just talking about creating patterns. We're talking about sculpting intricate masterpieces layer by layer. This level of flexibility not only pushes the boundaries of creativity, but fundamentally transforms the prototyping and low-volume production landscape. Here are examples of shapes where 3D printed wax thrives in investment casting manufacturing. Taking a quick look here, you can see some pivotal subcategories in engineering such as aerospace, automotive, architectural, and medical fields. A few of notice include automotive prototypes, consumer product prototypes, and customized jewelry designs.
Advantages in the context of 3D printed wax patterns are not just talking points. They're the drivers of innovation. Some of the key takeaways here are the design freedom, reduced lead times, and cost effectiveness in low volumes. The agility this technology brings to the design phase allows us to dance with creativity, swiftly adapting to market demands. Reduced lead times are not just about efficiency, they're about positioning ourselves in an ever-evolving landscape.
For every stride in innovation, there are hurdles to overcome. Material constraints and application limitations force us to reassess where 3D printed wax patterns may find their limits. Post-processing steps and the high initial setup costs are challenges that require our thoughtful consideration. In post-processing, it will require additional steps like polishing and machining in order to counter the rough surface conditions of 3D printed parts. In addition, this process is highly limited by production volume. Large demand for quick patterns are a key weakness to this process. Finally, build size limitations are another large consideration. Larger patterns may require multiple prints, introducing complexity, which result in higher costs and larger times.
This is a brief breakdown of the conventional process, highlighting the important benefits and considerations. Conventional wax patterns, formed through injection molding, offer us precision and consistency. This process is demonstrated in the image on the right-hand side. The tooling processes involved provide high efficiency in specifically large production runs. However, we must confront the challenges of lead times for tooling and the limitations in efficiently producing intricate designs.
Similarly, this presents the main points of the 3D printed process. The image on the right shows the major steps in the new 3D printed wax process we're talking about. If you look at the steps carefully, you can see it closely resembles the traditional way, but if we look on the left, we can see some key differences. First, we look at design flexibility. Due to the unparalleled design freedom, it allows for intricate and complex geometries, and material constraints may limit certain applications. Next, tooling independence. With the steps that are labeled on the right, we can see that it bypasses traditional tooling requirements and reduces setup costs. Rapid prototyping is also a key component to this, just in case you need to make a last-minute change. In addition, the adaptability at low volumes is also a great consideration, but be careful with higher volumes.
Here we perform a comparative analysis with costs as a central focus. Economics plays a pivotal role in our decision making. The cost considerations for conventional wax patterns revolve around substantial tooling expenses and longer lead times, impacting overall production costs. In contrast, 3D printed wax patterns offer advantages in terms of flexibility, adaptability to design changes, and lower tooling dependence. While 3D printing involves initial equipment costs, its suitability for smaller production volumes and rapid prototyping can result in cost effectiveness, especially in scenarios where design changes are frequent. The choice between the two methods should be driven by the specific production requirements, volumes, and the strategic goals of the manufacturing process.
Now, let's transition to the critical crossroads where theory meets reality. The Manufacturing Readiness Level, or MRL, assessment. This structured framework evaluates technology from concept to full-scale production. Technology demonstration isn't just about promises. It's about tangible, real-world proof. Through technology demonstration of this process, it receives a score of 8.5. Depending on the objective, the maturity of this process should be considered, as it is effective at low-rate production but falls short in high-rate production. The scoring criteria used for this assessment can be found in the table on Canvas.
These are the resources used to present the information you've witnessed today. All of these sources were obtained through Google Scholar.
Finally, I'd like to move to the discussion of resources and our bias assessment. Most of the sources we used in this study were purely informational and unbiased, but some of the sources we encountered included some bias. Of these bias articles/journals, they exhibited one of two biases. They either, one, contained a progressive view favoring the newer 3D printed process, or two, they were too harsh on the new process, refusing to reform to the newer side of manufacturing. Most sources we find these days, even on scholarly websites such as Google Scholar or here at Penn State through our libraries, have some sort of bias, and it's our job as engineers to sift through the bias and find out the truth.
In conclusion, we find ourselves standing at the crossroads of tradition and innovation, where the decision is not just about wax patterns, but about the trajectory of our manufacturing prowess.
We'd like to thank you for your attention, and together, let's forge a manufacturing future that aligns seamlessly with innovation and excellence.